Okay. And the last bit in our discussion on planar graphs is going to be to prove Euler's theorem, or at least say how one would prove Euler's theorem. Okay, so Euler's theorem, again, to remind you, says this. It says a planar graph. So for a connected planar graph, I should specify, we always have the number of vertices minus the number of edges plus the number of faces is equal to 2. Okay. Before I actually prove this, I want to point out that this is really a result from topology. And so, as I mentioned earlier, when we were picturing all of our Platonic solid friends, we were picturing these all as being drawn on a sphere. And so, what this theorem really is, at least the way I think about this theorem, this statement is a property of things on the sphere. If you draw something on a sphere, or if you break the sphere, if you want, into shapes, so you could, for example, break the surface of the sphere into into squares, or into pentagons, or whatever, or in some more complicated combination, like we'll talk later about a soccer ball, for example, which consists of hexagons and pentagons, that no matter how you do that breaking up of the sphere, if you count these three things, you will always get 2 out of this. So this 2 is often called the Euler characteristic of the sphere, because no matter how you break up the sphere, you'll get this 2. And it just so happens, and this is the reason why this is connected to planar graphs, that if you take the plane and you basically wrap the edges of the plane at infinity back to a point, then you get something that's shaped like a sphere. But every quote-unquote compact surface has its own Euler characteristic. And so for the sphere, that Euler characteristic is, as I said, 2. But if you take something like the surface of a torus, that Euler characteristic is 0. If you take a more exotic surface, and maybe I'll talk about this a little bit in a later video, like a 2-hole torus, then the Euler characteristic is -2, and so on. If you want, you can picture the surface of a Klein bottle, and you could ask what's the Euler characteristic of the surface of a Klein bottle, all of these sorts of things. And so there's an entirely different question, and I linked to a video about this in an earlier video. But there's an entirely different question about what graphs I can draw on the surface of a torus, or on the surface of a 2-hole torus, or whatever, and the answer works out to be completely different. There are other graphs that you can draw there. So for example, on the surface of a torus, you can definitely draw K33. I'll leave it to you to figure that out, or watch the other video. You can also draw K5, and again, I'll leave it to you to figure out how am I going to draw K5 on the surface of a torus. Okay, but how are we going to prove this? And the answer to how we're going to prove this is basically by induction. And so, what do I mean by induction in this instance? Well, I'm going to start with the simplest graph that I can think of, namely the graph where I have just one vertex and no edges. And so in this case, I've divided the plane into just one face. And so here I have one vertex, 0 edges, one face, 1 minus 0 plus 1 is 2, check. Okay, so this is my base case. Now, I'm going to assume now that I already have a graph where the conclusion of Euler's theorem is true. That is, on this graph, whatever happened, the number of vertices minus the number of edges plus the number of faces, it's identically 2. And so I'm going to imagine, what could I do to this graph to add another vertex to it. Well, let's see. If I'm going to add another vertex, remember I insisted that when I add another vertex, it has to be a connected graph, right? That is one of the hypotheses here in the theorem, is that the graph is connected. So I can't just add another vertex. So I have to connect that vertex to one of the vertices that's already in this imaginary graph here. And so when I do that, somehow I don't change the number of faces at all, because I just sort of stick this inside one of them. But what did I do to the number of vertices? Well, I increased the number of vertices by 1, but I also increased the number of edges by 1. And so I changed the number of vertices by 1, I changed the number of edges by 1, I did not change the number of faces. And so when I did that, what did I end up doing? Well, I changed the number of vertices minus the number of edges plus the number of faces by 0, because plus 1 minus 1 is 0. And so my conclusion here is that as long as the graph started out satisfying Euler's theorem, it still satisfies Euler's theorem. Okay, but that's not the only thing I could do. I could also start with my ghost graph, whatever it is, my graph that I started with that already satisfies Euler's theorem. And I could say, okay, instead of adding a new vertex, I'm not going to add a new vertex. I'm going to just connect two vertices that were already there, but that were not previously connected. And I'm going to ask, okay, if I do that, if I now connect two vertices that weren't previously connected, how does that change the number of vertices, the number of edges, and the number of faces? Well, it does not change the number of vertices, because I explicitly didn't add a vertex. It increases the number of edges by 1. Okay. But also I have to think about, what did adding this line here do? Adding this line here separated a face into now two faces, right? So it increased the number of faces by 1. And so if I did this of necessity, I now have this edge running across a face, and when that edge runs across the face, it separates the face into two faces. And so, like before, the number of vertices minus the number of edges plus the number of faces, it is still unchanged. Okay. Finally, what's the last thing I can do? Well, the last thing I could do is take an edge that's already in the graph and add to that edge a vertex in the middle. This is what we called a subdivision earlier in this lecture. So here, if I take the number of vertices, the number of edges, and the number of faces, and I ask, okay, what happened to the number of vertices? Well, I explicitly added one vertex, because I put a new vertex in the middle of this edge. What happened to the number of edges? Well, that also, of course, went up by 1, because this thing that was previously one edge is now two edges. And the number of faces, well, that did not change. So then, what do I have to do to convince you that this is enough to prove Euler's theorem? Well, I have to convince you that no matter what planar graph I want, I can start with this graph. That was my base case. And do one of these 3 operations. And with these 3 operations alone, I can get to any graph I want. So let's say here I want to get to the graph K4. So I'm going to try to make K4. Okay, so I'm starting here. I know Euler's theorem is true for this graph, because it has one face and one edge. And now if I convince you that I can make these 3 steps in some order to make a K4, then I will be done. Okay, so first of all, by step 1, I'm going to reach out and add a new edge and vertex. Okay. So this graph now, by our effectively inductive hypothesis, really we have 3 inductive hypotheses here, and our base case is this dot, so it's a little weird of an induction. But our base case plus our first inductive hypothesis here shows me this still satisfies Euler's theorem. Okay, I want to add another vertex here. So that is step 1 again. This still satisfies Euler's theorem. Sorry, I put that a little off the bottom. Okay, I'm going to now do that one more time. This still satisfies Euler's theorem. And so far, all I've done is use the thing I called 1, where I grab a vertex I already have, and then put on a new vertex and attach it to that. But now, in order to continue, I have all the vertices, so I can't add any more vertices. But I can now add this edge. And so by inductive hypothesis 2, when I add this edge connecting 2 already existing vertices, it still satisfies Euler's hypothesis, or sorry, it still satisfies Euler's theorem. Okay, then what else do I have to do? Well, I need an edge here. Okay, so that again is 2. I connected 2 vertices. Okay, and notice both of these step 2s that I did, they both increased the number of faces by 1, because in this case, once I drew this vertical line in, it separated the outside and the inside of the square. And then once I added this one, it separated the square into 2 triangles. And then lastly, I need to connect this piece to this piece. That's still a step 2. And so here, I think you'll probably believe, as long as the graph is connected, I can actually use only step 1 and 2 in combination to get any graph that I want. But I went ahead and threw in step 3 just to convince you, because that gives you a little more flexibility. But this proves that for every finite graph, Euler's theorem is true. And of course, if your graph isn't finite, then Euler's theorem doesn't even have a meaning, because if your graph isn't finite, then these numbers are infinity, and certainly you can't add and subtract a bunch of infinities and somehow get 2. Okay, so that's what I have to say about planar graphs for now. But later, when we talk about graph colorings, we're going to come back and talk more about planar graphs, and we're going to talk about what makes planar graphs special in the context of colorings, because you may have, for example, heard of the 4-color map theorem, and the 4-color map theorem says something about colorings, which we have not yet defined, of planar graphs, which we have now defined. So stay tuned, there is more to come on this topic. But until next time, be well.